Okay, let's look at the concept of impedance. And the impedance is basically extension of the concept of resistance. Now, since we have the capacitance and the inductance, also we can use algebraic equation to describe the element constant. Now we can kind of do the generalized impedance concept. And let's see if I have voltage, phasor, and current phasor, and that's the element. So if this voltage, phasor, and current phasor, and we have Z for this element, this is Z is impedance. Z is impedance. And you can think about impedance almost as, similar to resistance, but now since V and I are complex, are phasors, complex numbers, and so Z is complex typically, right? Z is complex, so this is different from the resistance. But sometimes it's hard to wrap your head around this concept intuitively, right? How this complex thing really do, right? The complex number has the magnitude and phase angle, even for the impedance. That means if the impedance is complex, the voltage current most likely they are not going to be in phase, right? So in addition to their magnitude different and skewed by the impedance and also the phase angle. So that's how this really related back to the signal in time domain. So for resistance, we have Z sub R is just R, right? For inductance, we have Z sub L, that's J omega L. And for the capacitance is 1 over J omega C, right? And so this is impedance. And also we have the concept of Y called admittance. I didn't put this in the Google Colab notes, but this also, but we're going to introduce this admittance. We're going to talk about the admittance in the S domain as we go to Laplace transforms. And the Y is the admittance. Admittance is similar to the concept of conductance. Again, here Y is complex. So in that case, Y is the I is equal Y times V. So you can think about the conductance. If more conductive, you get this higher current and with the same voltage. So therefore, the current actually proportional to the admittance. And in this case, the Y sub R is just so Y is the inverse impedance. So Y sub R is 1 over R, and the Y sub L is equal 1 over J omega L, and Y sub C for capacitance admittance is J omega C. You invert that Z sub C, right? And the admittance, as we do the parallel and the connections, we will see the admittance make the equation more compact and intuitive also. So most of us kind of more intuitive connected with the Z and less intuitive connected with the Y, but we should make friends with Y as well. Okay, that's the concept of impedance. Let's get to a simple example and see, hey, you talk about so much about these phasors. Let's see, show me the example. Okay, this example, a simple example we can use. I pre-drew this some circuits to save some time on the video clip. So let's see if I have the voltage in given this 10 volts and find the current in steady state. I have 1 ohm resistor, 1 millihenry inductance. And what you normally do with in 201, you would write the differential equation, the first order differential equation, you solve the differential equation and find the steady state solution for that, right? So in this case, I want to use the phasor, the new tool we just introduced in the last lecture, right? And the one we had in the impedance. So we want to convert this circuit to the phasors. So we convert the voltage and current to phasor voltage and phasor current, and we convert the elements to impedances. And so the resistance we have Z sub R. So now I drew this circuit. So the voltage here is, the phasor is just a 10, right? Because the phase angle is 0. You can write 0, or you can just don't write that 0 angle. So, and Z sub R is just R is equal 1 ohm. And Z sub L is J omega L, where the omega is based on this given here. This is the omega equal 1,000 radian per second. We should be always vigilant about the difference between omega and F. Right? And in one of the lectures, the last part of the lecture I got the error I had in that video was the T is equal 2 pi over omega, not omega over 2 pi. Omega over 2 pi is F. Okay, omega over 2 pi is F. And this Z sub L is J omega L, which is the J times 1,000 times the 1 millihenry, which is 0.001, which is J, right? So therefore, I can write the current. So the current here in terms of phasors, that's going to be the current through this one plus this one here. So that's just the KCL here, right? So I'm using the third flavor of the KCL. The annual currents equal the leaving currents. So the leaving currents is V over Z sub R plus V over Z sub L, right? So in this case, I got a V over, I can factor V out, right? The V is, actually I can put numbers in. V is a 10 times, so 1 over Z sub R, 1 over 1, that's the 1, plus 1 over J, that's a negative J, right? So therefore we have 10 times 1 minus J. 1 minus J, we would like to convert this to the polar form so that we know we will have, so the polar form here is, I have 1 here, I have a negative J here. So the phasor is sitting somewhere here, right? So the I is sitting in the fourth quadrant. So in this case, the phase angle would be negative 45 degrees. The magnitude is square root 2, so I have 10 times square root 2 negative 45 degrees, right? So that's the, in this case, if the voltage is here, right, and actually the current is lagging this voltage, which is very typical for what we call the inductive load, right? Z sub L, and so since this is inductance, this is inductive load, and the current is lagging the voltage, which is the very common on the power system as well, because since most of the loads are inductive. And now I can go back to the time domain by converting this. So this is the magnitude, which will be the amplitude of the current, 10 times square root 2, and the same frequency, and that's going to be omega 10,000. So omega is the phase angle, which is minus 45 degrees, right? So this is the answer. We don't really need any differential equation we can solve. We know the solution right away. So that's the usefulness of the phasor. I hope I fully convince you at this moment. I think that will conclude the lectures. If you like the video, make sure you subscribe to this channel, keep the channel grow, and also if you have some comments, leave at the comment down below, and I will see you next time.